Hi, this is Math 2520, and this video is over section 8.9. We are going to be looking at improper integrals. And for improper integrals, consider a definite integral that goes from a to b with its limits of some function. We say a or b are finite, and f of x is considered bounded. But let's consider a region bounded by x equals 1 and y equals 1 over x squared and y equals 0. Something like the graph below. We have to ask ourselves what happens if one of the boundaries goes to infinity. All right, and so one things we can do is we can look at this and write the area as a of t equals infinity from 1 to t of 1 over x squared dx, and let t go to infinity. That's kind of the formal way of writing this. And so if we have a to t then of a function, and exists for every number t greater than a, then we can look at the integral of a to infinity of f of x dx is the limit as t goes to infinity from one side, provided this limit exists as a finite number. We can also look at it if t goes to infinity, t goes to b as your limits of a function for your integral, while t is less than or equal to b, then the integral as negative infinity to b is the limit as t goes to negative infinity of this integral with limits t to b. Okay, again, providing these limits exist. All right, we call these integrals that have the infinities as part of the limits improper integrals. They are convergent if the limit exists and divergent if the limit does not exist, which means if they're convergent, they go to a number. If they are not, they go to infinity or negative infinity. And then if both the integral as a goes to infinity and the integral as negative infinity goes to a are convergent, then the integral from negative infinity to infinity of a specific function is going to be equal to the sum of those two integrals and will be convergent. Alright, sorry. So let's look at the integral from 1 to infinity of 1 over x squared dx. And we're going to look at this as a limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. And it's going to be limit as t goes to infinity. And then we do the antiderivative, and so you get negative 1 over x, and this goes from 1 to t. And so it'll be the limit as t goes to infinity of negative 1 over t plus negative 1 over 1. Oh, I'm sorry, minus negative 1 over 1. I gotta subtract the bottom. That's going to make it a plus. So limit as t goes to infinity, negative 1 over t plus 1. Okay, now as t goes to infinity, this negative 1 over t goes to 0. And so this ends up being equal to just 1. Okay, so, we replace the infinity sign with t in order to do the antiderivative and to do the limits, and then we let t go to infinity. It's basically what the process is. Not much different than taking a integral with a variable in the limits. Right, so let's say we have an integral from negative infinity to 0 of of x e to the x dx. Right, so we'll write this as the limit as t goes to negative infinity of the integral t to 0 of x e to the x dx. And now we have to do integration by parts, so we'll let u equal x, and so du equals dx, and dv equals e to the x dx, so v equals e to the x. And so this becomes the limit as t goes to negative infinity of x e to the x evaluated from t to 0 minus the integral from t to 0 of ex dx. This is uv minus v du. Okay. So we can do the integral of e to the x dx. So you get e to the x from t to 0 minus e to the x from t to 0. Right, now evaluate these. We'll get a limit as t goes to infinity, negative infinity, of 0 e to the 0 minus t e to the t minus e to the 0 minus e to the t. Alright, so we'll simplify this first. This is 0. We'll have a negative t e to the t minus e to the 0 is just 1. Oops. I don't know why I just did. Hit the wrong thing. Minus 1. And then plus e to the t. Yeah, and then we'll let our t go to infinity. Actually, let's simplify this some more, not much more. I'm going to pull out a e to the t. Actually, I'm going to pull out negative e to the t. We'll have t minus 1. So this e to the t on the right here becomes negative 1. And I pull out negative e to the t. And then t e to the t becomes just positive t. And then minus 1. Alright, so now e to the t, that to the negative, is going to go, if you think about the graph of it, e to the negative t goes it's a downwards. So downwards like this. And so as this goes to I'm sorry, hold on. That's e to the t, not negative e to the t. So it goes up like this. Oops. This is e to the t. The negative, we don't need a negative up there. the negative of this will make it go down this way. That's negative e to the t. So as this goes to negative infinity, which is this direction, it's going to 0. Right? So this sign is going to 0, which takes this whole thing to 0. And a whole thing, I mean, this section takes that whole section there to 0. And so this goes to negative 1. All right. Now let's look at from negative infinity to infinity of 1 over 1 plus x squared dx. And for this, we look at the limit as t goes, well, actually, we want to call that a different letter. I want to say a. What's this? Saves. It's going to be a going to negative infinity. The integral of a to c of dx over 1 plus x squared, and plus the limit as b goes to infinity of c to b dx over 1 plus x squared. Right. This is going back to this formula here, negative infinity to a. We'll just basically, we'll call on this c instead, and we're letting a go to negative infinity, and then b goes to infinity. That's all we're doing. All right. Right. The antiderivative with 1 dx of 1 plus x squared, or 1, I'm sorry, dx over 1 plus x squared, that is your inverse tangent. Okay, you can go look back up. That is inverse tangent. So we have limit as a goes to negative infinity of inverse tangent of x, evaluate from a to 0, and then the limit as b goes to infinity of inverse tangent of x, evaluate from 0 to b. Zero being that break between them. Okay, so with this, we're evaluating. Oops, oh, with the integral. I meant the evaluation sign here. Okay, so we'll have the limit as a goes to negative infinity of inverse tangent of 0 minus inverse tangent of a plus the limit as b goes to infinity of the inverse tangent of b minus the inverse tangent of 0. Okay. Inverse tangent of 0, angle 0 gives you that, so that ends up being 0 in both of these cases. And so we'll have limit as a goes to infinity of the negative inverse tangent of a, it's limit as b goes to infinity, this one should be negative infinity, of tangent inverse of b. Right, so on a graph of inverse tangent, it looks like this. And this is going from negative pi over 2 to pi over 2. So as a goes to a negative pi over 2, or a goes to negative infinity, the inverse tangent goes to negative pi over 2. Right, so that would be this first one, be negative pi over 2. Negative from this negative here. Alright, that's the limit as a goes to negative infinity. And then as inverse tangent goes to infinity, as b goes to infinity, inverse tangent goes to pi over 2. So we have just a positive pi over 2. So we'll have pi over 2 plus pi over 2, which is just going to be equal to pi. I'll write that as soon as it saves. And so that'll be equal to pi. Okay. Now, there's another type of improper integral called type 2. This is discontinuous integrands. If f is continuous from a to b and is discontinuous at b, then the integral from a to b of f of x is equal to the limit as t goes to b from the negative side of the integral a to t f of x dx, if this limit exists as a finite number. And the other part of this is if it's continuous from a to b and discontinuous at a, then the integral from a to b of the function is the limit as t goes to a from the positive side of the integral t to b f of x dx. Again, if this limit exists as a finite number. And again, if it's if this integral is convergent, then your limit will exist and you'll get a value out. If it's not, and it's divergent, the limit doesn't exist. And then the last part of this is if f has a continuity at c, where c is between a and b, and then both integral from a to c and integral from c to bx are convergent, then we have the integral from a to b of f of x dx is the sum of those two. Alright, so say we have the integral from 0 to 2 of 2 over x minus 1 cubed dx. And at x equals 1, we have a discontinuity. Because we end up dividing by 0. Okay, so we're going to have the limit as t goes to 1 from 0 to t of 2 over x minus 1 cubed dx plus the limit as t goes to 1 from t to the 2 of 2 over x minus 1 cubed dx. Okay, so we're saying the limits from 0 to t and from t to 2 because of that discontinuity at 1. Alright, so we have to look at the antiderivative for this first. So we'll have the limit as t goes to 1 of negative 1 over x minus 1 squared. And this is going to be from 0 to t. Okay, that's the antiderivative because if you take the derivative of that, you have a negative 2 on the top for your power. That will come down, giving you a positive 2 in the numerator. and then your power for that drops to -3, and so you end up with x minus 1 cubed on the bottom. And basically just take the derivative of what I just did, and you'll get what you have in the previous one. And then this will be plus limit as t goes to infinity, or I'm sorry, t goes to 1 of -1 over x minus 1 squared evaluated from t to 2. Alright, so we'll do the limits. I'm sorry, we'll do the integral. Those are called limits too. Anyways, so -1 over, let's do this, limit as t goes to 1, -1 over t minus 1 squared minus -1 over -1 squared. Because the 0 minus 1 is -1 squared. Alright. And plus -1 over 2 minus 1 is 1 squared minus -1 over t minus 1 squared. Okay. So simplify some of this. Well, -1 over t minus 1 squared plus -1 squared is just 1, so it'd be plus 1. And then minus 1. And then plus 1 over t minus 1 squared. Alright, so the 1's cancel. Add the 0. However you want to say that. Now, 1 over t minus 1 squared. As t goes to 1, this, and we're not going to involve the negative sign here, this goes to infinity, and same with this one. So these go to infinity, okay, because this is going to 0. So this is actually divergent, where one side goes to negative infinity, the other side goes to infinity. Right, and so we get divergent. All right. So now let's say we want to find the area of a region bounded by y equals cube 1 over the cube of x, y equals 0, x equals 0, and x equals 1. So let's graph this. So 0 to 1. At 1, you get 1 over 1, so that would be equal to 1. And then at 0, it goes, you have that, it'd be divided by 0, so it goes up like this, like an asymptote. And so the area we're looking at is this area here, as this is going to 0. And so we have the limit as t goes to 0, t to 1, x to the -1/3 dx, which is going to be equal to the limit as t goes to 0. We'll do the antiderivative here. We'll get 3x to the 2/3 over 2. evaluate from t to 1. This will be the limit as t goes to 0. 3/2 minus 3t to 2/3 over 2. Okay. Now we apply the limit t to 2/3, that when t goes to 0, that goes to 0. So this whole thing goes to 3/2. This basically is equal to 0. All right. Last problem we want to know is the integral from 2 to 3 of 2 over x minus 1 cubed, an improper integral. Right, so x cannot equal 1. That's what the discontinuity is. But 1 is not in the region from 2 to 3. So there does not exist a discontinuity from 2 to 3. Therefore, this is not an improper integral. Yeah, so, but this discontinuity is not in the region from x equaling 2 and x equaling 3. Okay, also, both upper and lower limits are not at infinity. Okay. Therefore, this is not an improper integral. To do this integral, we would just do it normally. 2 to 3 of 2 over x minus 1 cubed dx. Take the antiderivative. Oh, actually, let me rewrite this. Integral from 2 to 3 of 2 x minus 1 to negative third dx. And we take the antiderivative, you get negative x minus 1, negative 2. And evaluate this from 2 to 3. So we'll have negative 3 minus 1 to negative 2 minus a negative 2 minus 1 to negative 2. Right, so this would be, I'm going to move these to the numerator or the denominator. So negative 1 over 2 squared plus 1 over 1 squared. So negative 1/4 plus 1 be 3/4. Okay, no need for limits as t going to infinity because it's not an improper integral. Alright, in the next chapter we'll be looking at lengths and areas and using integrals to find them of different curves. And I'll see you then. Bye.